Welcome back to the Deep Dive. Today, we're taking one of those invisible systems we rely on every single day, the notification system, and really unpacking the engineering needed to make it work.
It's absolutely fundamental, isn't it? That little ping on your phone or the email alert, it seems so simple.
Right. But making sure that ping arrives, whether it's breaking news, a shipping update, or just a reminder, well, that's where the complexity starts.
Especially when you think about the scale involved. We're not just sending a few messages.
Exactly. So today, our mission is to understand how you actually build one of these systems. We want to get into the architecture needed for something that handles millions of users, stays reliable, and crucially, respects the user.
And the requirements we're looking at today are, well, they're significant. We're designing for three main types of notifications.
Okay, what are we dealing with?
Mobile push notifications, your standard SMS messages, and of course, email.
Three distinct channels right off the bat. And the scale. Let's nail that down because, as always, scale changes everything.
It really does. For this system, we need to plan for 10 million mobile push notifications per day.
10 million push alone. Okay.
Plus 1 million SMS messages, and another 5 million emails daily.
Wow. Okay, so that's 16 million messages combined every single day.
16 million. And these aren't optional, nice-to-have messages. Many are critical.
So given that volume, what's the speed requirement? Do these need to be absolutely instantaneous?
It's what we call a soft real-time system. The goal is definitely ASAP delivery. You want latency in milliseconds, ideally. But the architecture needs to be smart enough to handle huge spikes. So slight delays under very high load are acceptable. That soft part is key. It lets us use asynchronous processing, which is essential for scaling.
Got it. And device support. It has to work everywhere people are.
Absolutely. iOS, Android, and also laptops or desktops via web notifications.
And what triggers these? Is it always the user doing something?
Not always. It can be client-initiated. Maybe you tag someone in a photo that triggers a notification. Or it can be server-side. Think scheduled things like daily news digests, billing reminders, system updates, that kind of thing.
And one last crucial piece you mentioned, user control.
Non-negotiable. Users must be able to opt out easily. If someone says no more marketing emails, the system has to honor that instantly. No leaks.
Because if you annoy users, they just turn everything off.
Exactly. You lose the channel completely. It's about respecting their preferences.
Okay, let's unpack this then. We're going from the simple idea, send an alert, to designing something distributed, resilient, handling 16 million messages across different platforms in soft real time. It's quite a challenge.
It is. And the first step is understanding the different ecosystems we need to talk to.
Right. So those three channels, push, SMS, email, they don't work the same way. We're relying on external systems, aren't we?
Heavily. As soon as you send something outside your own network, you introduce dependencies. Let's start with mobile push, maybe iOS first. It feels like the most controlled environment.
Okay, yeah. How does an iOS push notifications actually get delivered?
So for iOS, you need three main players. First, there's our service, the provider. That's us generating the notification.
We decide what to send.
Right. Then the provider sends the request not directly to the phone, but to the second player, the Apple Push Notification Service, or APNS.
That's Apple's intermediary.
Exactly. It's the secure gateway. And to talk to APNS, our provider needs two critical things. First, the unique device token. It's this long, opaque string that identifies the specific device.
Okay, so that tells APNS where to send it.
Precisely. And second, you need the JSON payload. That's the actual content, the message, text, sound, badge number, maybe some custom data.
And this goes over a secure connection.
Yes, typically HTTP2 now. It's secure and persistent. Then APNS, the third participant, takes over.
And APNS is the one talking to the actual iOS device.
Correct. APNS manages that connection. This is really important for things like battery life. APNS can batch notifications, deliver them efficiently, wake the device only when necessary.
So we, as the provider, don't have to worry about managing connections to millions of individual iPhones.
Thank goodness no. APNS handles that complexity. We also tell APNS the priority. A critical alert gets high priority, meaning deliver now. A less urgent update might get low priority, so APNS can wait for a better time, like when the device is already active, saving battery.
Makes sense. And Android. Similar idea, different vendor.
Pretty much. Android uses Firebase Cloud Messaging, or FCM, Google's equivalent.
Okay.
The flow is almost identical. Our provider sends the request, including the Android device token and the payload, to FCM. FCM then manages the deliver to the Android device.
No, for mobile, we're completely reliant on APNS and FCM.
Right.
No way around them.
None at all. They ensure security, efficiency, and adherence to platform rules. You have to play in their sandbox.
Right. Now, SMS and email. Here, we don't have Apple or Google dictating terms quite so directly.
Yeah.
Why still lean on third-party services? Why not send SMS ourselves?
Oh, that's a deep rabbit hole. For SMS, it's about infrastructure and regulations. Building and maintaining connections to every mobile carrier globally. It's a massive undertaking.
Dealing with all their different rules and throttling.
Exactly. Services like Twilio or Nexmo, they've already done that hard work. They handle carrier relationships, number provisioning, compliance, and they help ensure your messages actually get delivered without being flagged as spam. They abstract away enormous complexity.
Okay, so outsourcing the telecom nightmare makes sense for SMS. What about email? 5 million a day is a lot, but couldn't we run our own mail servers?
You could, but it's usually a bad idea at scale. The biggest issue is IP reputation.
Right. If your server's IP address gets a bad reputation.
Your emails go straight to spam. All of them. Sending 5 million emails daily makes you a huge target for spam filters. Services like SendGrid or MailChimp specialize in maintaining high IP reputation. They manage dedicated IP pools, handle bounce and complaint processing, and implement authentication standards like DKIM and SBF.
Things that prove your emails are legitimate.
Exactly. They also give you crucial analytics. Delivery rates, open rates, click rates. Getting that data reliably from a self-hosted setup is really, really hard.
So we're basically outsourcing deliverability and trust for email, just like we outsource the carrier complexity for SMS.
That's a good way to put it. We're integrating with potentially 5 major external systems: APNS, FCM, an SMS provider like Twilio, and an email provider like SendGrid, each with its own API, its own rules.
Okay, but before we can send anything through any of these, we need the addresses, right? The device tokens, phone numbers, email addresses.
Absolutely. That brings us to the contact info gathering flow. You need the right data foundation.
How does that work? When does the system get this info?
Typically, it starts when the user installs the app, registers on the website, or maybe explicitly opts into a specific notification channel within the app settings.
And that data flows into our system.
Right. Our main application servers, the API servers, collect this info, email, phone number, and importantly, the device tokens generated by the mobile OS. And this needs to be stored carefully.
How should we structure that data? Especially considering one user might have multiple devices.
That's key. You can't just stuff everything into one big user record. You typically have a user table with stable info, like email and phone number.
Okay.
And then a separate device table. This table links back to the user read, but stores those specific, potentially temporary device tokens from APNS or FCM.
So one user ID could have multiple entries in the device table, one for their phone, one for their tablet.
Exactly. So when we need to send a push notification to user 123, the system has to query that device table, find all active tokens associated with user 123, and potentially send the same notification payload to each of them via APNS or FCM.
That one-to-many relationship is critical.
It is. And one more point on those device tokens, they aren't permanent.
Right, they can change.
Yes. If a user uninstalls and reinstalls the app, or sometimes just over time, APNS or FCM might issue a new token or invalidate the old one. Our system needs a feedback loop, usually from APNS FCM, to know when a token is no longer valid so we can clean it up. Otherwise, we waste effort sending messages to dead ends.
Okay, so data gathering, careful storage, and managing token lifecycle are prerequisites before we even send the first message.
Now let's circle back to that initial simple design idea. One server trying to do everything. We know the scale 16 million a day. Why is this simple approach doomed to fail?
Right, the monolith. You have various services, billing, messaging, whatever, all calling this single notification system box.
Yeah.
And that box does the database lookups, builds the message, talks directly to Twilio, APNS, SendGrid. Feels clean, but brittle.
Extremely brittle. We identified 3 main reasons why this just falls apart at scale. Catastrophic problems, really.
Okay, what's the first most obvious one?
The single point of failure, or SPOF. If that one notification server crashes, hardware failure, bad deployment, network glitch, anything, what happens?
Everything stops. All 16 million notifications for the day, dead silence.
Exactly. You have zero redundancy. That's completely unacceptable for any critical system, let alone one handling this volume.
Okay, SPOF is bad. What's next? Even if it stays online, it sounds like it's doing a lot of heavy lifting.
It is. And that leads to the second problem. It's hard to scale independently. That single server is juggling multiple tasks. Database queries, maybe caching, rendering HTML emails, encrypting push payloads, making network calls.
All mixed together.
Right. So if you suddenly get a huge spike in email volume that requires more CPU for HTML rendering, it might starve the resources needed for processing push notifications. You can't scale just the email part or just the database part. You have to scale the entire monolith, which is inefficient and often leads to resource contention.
You end up over-provisioning everything just to handle the peak demand of one component.
Precisely. And the third killer is related to those external calls.
Talking to APNS, Twilio, etc. They aren't always instantaneous.
No, they're not. And that's the performance bottleneck. Building the notification content takes time, sure, but waiting for responses from third-party services is often the biggest delay. If your server makes a synchronous call to SendGrid to send an email, it has to sit there and wait for SendGrid's API to respond.
And if SendGrid is having a slow moment,
that server thread is blocked. It can't do anything else. Now multiply that by millions of requests per day. Very quickly, all your available connections or threads get tied up, just waiting, and the entire system grinds to a halt. Even if the server itself is powerful, it gets choked by external latency.
Okay, so the monolith is out, SBOF, scaling problems, performance bottlenecks. This forces us into a different approach. Distributed, asynchronous.
Exactly. Here's where it gets interesting. We need to break it apart, add redundancy, and crucially decouple the components.
How do we start?
First, address the SPOF and scaling. We achieve horizontal scaling. Put multiple notification servers behind a load balancer. If one fails, traffic routes to others. If load increases, add more servers. Simple.
Makes sense. Get rid of the single point of failure.
Second, externalize data. Move the database and cache out of the notification servers. Let them be separate, scalable services that the notification servers can query.
So the servers become more stateless, focused on processing.
Right. But the real magic, the thing that solves the bottleneck and decoupling problem, is introducing message queues.
Ah, the buffers.
Yeah?
Like Kafka, RabbitMQ, SQS.
Exactly. These queues sit between the services that request a notification and the services that actually send it. They play two vital roles.
Okay, what's the first role?
Decoupling. When Service 1 wants to send an email, it doesn't call the email sending logic directly anymore. It just formats a small message and instruction and drops it onto the email message queue.
And then Service 1 is done, it moves on immediately.
Instantly. It doesn't wait for the email to be sent or for SendGrid to respond. This keeps the triggering services fast and resilient. They're decoupled from the notification delivery process.
Okay, decoupling is huge. What's the second role? Buffering.
Buffering, yes. Imagine that massive spike we talked about. 5 million push notifications need to go out right now. The old monolith would just collapse.
Right.
With queues, the notification servers can quickly take all 5 million requests, turn them into queue messages, and stuff them into the press notification queue. The queue acts as a giant buffer, holding these messages safely.
And the actual sending happens later at a sustainable pace.
Exactly. The workers that process the queue can pull messages off at a rate they can handle, smoothing out the burst. The queue absorbs the shock.
That makes handling unpredictable load possible. Now, you mentioned email queue, push queue. Are we using separate queues?
Oh, absolutely critical optimization here. You cannot just have one giant queue for all 16 million messages. That reintroduces coupling.
How so?
Think about it.
Mm-hmm.
We need distinct message queues for each notification type. An iOS PN queue, an Android PN queue, an SMS queue, an email queue.
Okay, 4 separate queues. Why is that isolation so important?
Let's use that scenario.
Yeah.
Your SMS provider, Twilio, has a major outage. Their API is slow or failing. If all messages were in one queue, the workers pulling from that queue would grab an SMS message, try to send it, fail, maybe retry, and get stuck.
Blocking everything behind it.
Exactly. While the workers are struggling with failed SMS messages, the queue fills up, and critical emails or push notifications just sit there unprocessed, waiting behind the roadblock.
Ah, I see. But with separate queues.
The SMS queue gets backed up, yes. The SMS workers might struggle, but the workers dedicated to the email queue, they keep pulling email messages. The iOS push workers keep pulling iOS messages. The outage in one channel doesn't affect the others.
That's huge for reliability.
That's
Isolation prevents cascading failures across channels.
It's fundamental, so this gives us a much more robust workflow. Let's walk through the steps now with queues in place.
Okay, the optimized flow. Step 1.
Step 1. A service, billing, user action, whatever, decides a notification is needed. It calls the notification API, which is hosted on our horizontally scaled notification servers behind the load balancer.
Step 2. The notification server receiving the request does the initial work. It fetches necessary data user info, device tokens, and critically, checks the user's notification settings from the external cache or database.
Filter out opted-out users early.
Step 3. Assuming the user should receive it, the notification server doesn't send the notification itself. It constructs a queue message, an instruction. This contains maybe a unique event ID, the user ID, template information, parameters, and places this instruction onto the correct message queue, iOS PN, Android PN, SMS, or email.
And at this point, the notification server's job for this request is done. It sends a success response back to the original calling service.
Fast and decoupled. Step 4.
Step 4, we have separate pools of workers. These are independent services, often simple processors. You have email workers watching only the email queue, iOS workers watching only the iOS PN queue, and so on. They pull instruction messages from their designated queue.
Specialization. Step 5.
Step 5. The worker takes the instruction message. It might fetch a template, render the final content, like the HTML email or the JSON push payload, and then makes the actual call to the appropriate third-party service SendGrid, APNS, FCM, Twilio.
So the worker is the one actually talking to the outside world.
Yes. And finally, step 6. The third-party service takes it from there and delivers the notification to the end user's device. Our system might get an asynchronous callback or status update later, but the main flow is complete.
Okay, that feels much more robust. Scalable servers, external data, and specialized queues and workers providing decoupling and resilience.
Exactly. But this distributed asynchronous design introduces its own set of challenges, particularly around guaranteeing delivery and avoiding duplicates. We've made it scalable, and now we need to ensure it's truly reliable.
Right. We said notifications can be delayed, maybe even reordered slightly because of the queues, but they absolutely cannot be lost. If a worker crashes mid-process or a queue has a temporary glitch, how do we prevent that message instruction from just vanishing?
Persistence is key. We need to ensure that once a notification request is accepted by our system, it's stored durably until successful delivery is confirmed or it's definitively failed after retries.
So where does that persistence happen?
We introduce another component, a dedicated notification log database. When the notification server generates that instruction message in step 3 and puts it into the queue, it also reads a record to this log database. This record contains the unique event ID, the target user, the channel, the parameters, and initially, a status like queued.
So even before it's processed, there's a permanent record that we intended to send this notification.
Precisely. This log database becomes our source of truth, our audit trail. If anything goes wrong later, a worker crashes after pulling the message, but before confirming delivery, we can use this log to know we still need to process that event ID.
That sounds potentially huge. Logging 16 million events daily, forever? What's the justification for that overhead? Is it just for recovery?
It serves multiple purposes. Recovery is one, yes. It allows us to build a robust retry mechanism. But it's also crucial for auditing and compliance.
How so?
Imagine a user claims they never received a critical payment failure notification. With the log, we can look up the event ID and prove exactly when the instruction was created, when it was sent to the third party, and what response we got back. This is vital for disputes and regulatory requirements.
Okay, so it's a system of record, and it feeds the retry logic.
Yes. If a worker fails to send a message, it, or a separate monitoring system, can update the status in the log and potentially re-queue the message based on the log data.
Got it. Now, retries and the nature of distributed systems bring up the opposite problem, duplicates. We retry to avoid losing messages, but that means sometimes the user might get the same message twice. Can we guarantee exactly one's delivery?
The holy grail. In a system this complex, involving multiple internal services, queues, workers, and external third parties, true, provable exactly, once delivery is practically impossible without sacrificing performance significantly.
So what do we aim for?
We aim for at least once delivery, meaning we guarantee the message gets processed at least once, potentially more, combined with a strong dedupe mechanism on the receiving end to catch and discard duplicates before they're sent.
Okay, so we accept duplicates might occur internally, but we try to filter them out. How does that deduplication work?
It relies heavily on that unique event ID we generate back in step 3 and store in the log.
Right. Every notification attempt has a unique ID.
Yes. So when a worker picks up an instruction message from the queue, its very first action, before doing any real work, is to check if it has processed this specific event ID recently.
How does it check? Where does it look?
Typically, you'd use a fast shared storage system like a distributed cache, think Redis or Memcached. The worker performs an atomic check and set operation. Have I seen event ID XYZ in the last, say, 48 hours?
Okay, if Redis says, yes, I've seen it.
The worker immediately discards the message and acknowledges it off the queue. It assumes the previous attempt either succeeded or is still in progress, duplicate detected and dropped.
And if Redis says, no, haven't seen it.
The worker then immediately writes the event ID to Redis with a specific time to live, TTL, marking it as seen or processing, and then proceeds with actually building and sending the notification.
That makes sense. The key is that atomic check and set. But what about that TTL? How long do we remember an event ID?
That's a critical tuning parameter. Too short, and a delayed message might arrive after the TTL expires, causing a duplicate. Too long, and your Redis instance consumes vast amounts of memory storing old IDs.
Finding the sweet spot.
Exactly. It needs to be long enough to cover reasonable network delays and retry windows. Often something like 24 to 72 hours is a common choice, depending on the system's specifics.
Okay, so we log for persistence and retry, and we dedupe using unique IDs and a cache to manage the at least once reality. Yeah, let's talk about the content itself. Building 16 million unique messages sounds slow and error-prone.
It would be impossible. That's where notification templates come in. You don't construct every shipping notification from scratch.
Right. You have a standard format.
Exactly. Templates are predefined structures for recurring notification types, password resets, order confirmations, new message alerts. They contain the standard text, styling, maybe placeholders for dynamic content, required links, branding, legal disclaimers.
So the template defines the shell, and the worker just injects the specific details, like username or tracking number.
Precisely. The instruction message that goes onto the queue doesn't contain the full rendered text. It contains the template ID and the variable parameters.
And the benefits.
Huge. First, consistency and reduced errors. The core message, styling, and links are defined once, correctly. Second, maintainability. Need to update the company logo or add a new legal footer to all order emails. You update one template, not millions of lines of code. Third, performance. Workers don't need to do complex rendering, they just perform fast string substitution.
Makes perfect sense for efficiency and quality control. Now back to the user. We have this powerful, efficient system, but we need to ensure we're not overwhelming people. User control is paramount.
Absolutely. Two key aspects here: explicit settings and implicit limits. First, notification settings.
The user's preferences.
Yes. We need that notification setting table we mentioned earlier, link of user id, channel, push, email, SMS, and an opt-in flag, true, false.
And this check has to happen early in the flow.
Critically early. Back in step 2, when the notification server gets the initial request, before putting anything onto a queue, it must check these settings. If the user has opted out of, say, promotional push notifications, that request is dropped right there. It never even makes it to the queue.
And that check needs to be fast, hence caching those settings.
Definitely. You can't afford a slow database query for every single incoming request. Cache user preferences aggressively. But even if a user is opted in, we still need to be careful not to flood them.
Right. Sending 5 friends liked your photo alerts in 30 seconds is annoying. This is where rate limiting comes in.
Exactly. Rate limiting or frequency capping. Just because a user allows push notifications doesn't mean they want 50 per hour. We need rules to prevent abuse or simply overwhelming the user.
How do we implement that?
Similar to deduplication, this often involves a fast cache like Redis. We might use algorithms like token bucket or leaky bucket. For each user, we maintain counters. How many non-critical push notifications has user 123 received in the last hour?
And if they hit the limit, say 10 per hour.
The notification server, again in step 2, checks this limit. If exceeded, it might throttle the notification, delay it slightly, or drop it entirely, depending on the configured policy.
But what about really important stuff? A fraud alert shouldn't be dropped because they got too many like notifications, right?
Absolutely. You need priority levels or categories for notifications. Critical transactional messages, fraud alerts, password resets, two-factor auth codes must bypass the general rate limits. Promotional or less urgent social notifications are subject to the strictest limits. This distinction is usually part of the metadata sent in the initial request.
Okay, user settings checked first, then rate limits applied based on priority. That covers user respect.
Oh.
What about system health itself? How do we know if this complex machine is actually working well?
Monitoring is key. And the single most important metric to watch is the number of queued notifications in each message queue.
The queue depth.
Yes, the queue depth. Under normal operation, if your workers are processing messages as fast as they're being produced, the queue depth should stay relatively low and stable.
But if it starts climbing?
If the number of messages in a queue starts growing rapidly and stays high, we call that queue backlog. It's a clear signal that your workers can't keep up.
What could cause that?
Maybe a sudden, massive burst of incoming requests, or maybe latency from a third-party provider like APNS getting slow, or simply not having enough worker instances provisioned.
So high queue depth is the fire alarm. It tells us we need to scale up the worker pool for that specific queue fast.
Exactly. Monitoring queue depth and having auto-scaling rules for the worker fleets based on that metric is crucial for maintaining that soft, real-time performance.
Makes sense. What about securing the entry point? How do we stop just anyone from injecting messages into our queues?
Good point. The notification API, hosted on those initial notification servers, needs to be secured. You can't have random services or potentially malicious actors triggering notifications.
How do we lock that down?
Typically, internal APIs like this are protected using an app key and app secret system. Each legitimate internal service that needs to send notifications is issued a unique key and secret.
And they have to include that with their request.
Yes. They usually use the secret to generate a signature, like an HMAC, of the request payload, and send the signature along with their app key. The notification server then uses the provided app key to look up the corresponding secret, recomputes the signature, and compares them.
If the signatures match, the request is authenticated. If not,
it's rejected immediately. Unauthorized access denied. This ensures only verified internal clients can trigger notifications.
Okay, authentication is handled. One last piece. Tracking effectiveness. We're sending 16 million messages. We need to know if they're actually achieving anything.
Right. Event tracking for analytics. This needs to be built in. When a worker successfully sends a notification, gets a success confirmation from APNS, SendGrid, etc., or even when a notification fails, it should ideally log this event.
Log it where? Back to the notification log DB.
It could update the status there, yes. But often, it also sends an event to a dedicated analytics service. This service aggregates data on things like delivery rates and potentially integrates with client-side tracking for open rates, click-through rates on links within the notifications, and downstream user engagement.
So we can answer questions like, did that promotional email campaign actually lead to sales? Or are users opening the password reset notification?
Exactly. This feedback loop is vital. It helps optimize templates, timing, channel choices, and measure the overall business impact of the notification system. Without tracking, you're flying blind.
Okay, we've journeyed from a simple, fragile server to this complex, distributed architecture. Let's try and pull it all together. Summarize the final, robust design we've landed on.
Right. So at the front door, we have our horizontally scaled notification servers. They act as the API gateway. Crucially, they now perform authentication using those app key app secret pairs to verify the caller, and they immediately apply rate limiting based on user ID and notification priority, and check user settings, opt-in, opt-out status, dropping requests that shouldn't proceed. This happens before anything hits a queue.
Protecting the system and the user right away, then the instruction goes into a specialized queue.
Yes, into one of the distinct message queues, iOS, Android, SMS, email. And simultaneously, a record is written to the notification log database for persistence and auditing.
Okay, logged and queued. Then the workers take over.
Specialized worker pools pull messages from their specific queues. Their first step is the deduplication check using the event ID against a cache like Redis.
Filter out duplicates if it's a new event.
They fetch the appropriate template, merge it with the parameters from the message, and construct the final notification payload. Then they attempt to send it via the relevant third-party service, APNS, FCM, Twilio, SendGrid.
Now, what happens if that send attempt fails? Let's say Twilio times out.
This is where the retry mechanism kicks in, powered by the log DB. The worker, or a monitoring system, detects the failure. It doesn't just give up. The message instruction is typically placed back into the message queue, or possibly a dedicated retry queue, to be attempted again later.
But not immediately, right? We don't want to hammer a failing service.
No, absolutely not. We use exponential backoff. The first retry might be after 5 seconds, the next after 30 seconds, then 2 minutes, 10 minutes, and so on. The delay increases exponentially with each failure,
giving the third-party service time to recover.
Exactly. We might configure it to retry, say, 5 times over a period of 4 hours. If it still fails after all those attempts.
Then what? Is it finally lost?
No. we still don't lose it. The message is then moved to a dead letter queue, DLQ. This is a special queue that holds messages that have exhausted all retry attempts. Alert is immediately triggered for the development or operations team.
So a human can investigate why that specific message failed persistently. Nothing gets silently dropped.
Correct. And all of this is supported by strong monitoring, especially queue depth, and integrated tracking sending events to an analytics service. It's a closed loop.
Wow. Okay, so that complete picture incorporates everything.
Yeah.
Scaling, decoupling, persistence, retries, deduplication, templates, user settings, rate limiting, security, monitoring, and tracking. It's quite the machine.
It has to be to handle that scale reliably and responsibly.
So stepping back, what does this mean for someone listening trying to wrap their head around system design? What are the big takeaways from building this kind of distributed system versus the simple approach?
I think there are a few key achievements that this architecture unlocks. First, reliability. Through the logging, the robust retry mechanism with backoff, and the DLQ, we've built a system where messages are effectively never lost due to transient failures. That's huge.
Okay, reliability first.
Second, scalability and resilience. The use of message queues for decoupling and buffering, combined with horizontally scalable servers and specialized workers, means the system can handle massive, unpredictable load spikes. And an outage in one component, like the SMS provider, doesn't take down the entire system.
Got it. What else?
Third, security and auditability. API authentication protects the entry point, and the notification log provides that immutable record for compliance and debugging.
Right. And the fourth?
And fourth, maybe most importantly from user perspective, user respect. Building in the checks for settings and rate limiting right at the start demonstrates that the system is designed not just to blast messages out, but to communicate effectively and considerately within the boundaries the user sets.
So it's about building trust with the user, not just delivering bits.
Absolutely. At 16 million messages a day, trust is everything.
It really is staggering when you lay it all out. All that complex engineering, multiple vendor integrations, async processing, distributed databases, caches, queues, retry logic, just to make sure that simple alert for your movie starting or your package arriving shows up reliably on your screen.
The best systems often hide the most complexity. When it works seamlessly, you don't even think about it.
True. Okay, let's leave our listeners with something to chew on. We talked a lot about reliability and the challenge of exactly once delivery. We settled on at least once plus deduplication as the practical approach.
Right, acknowledging that duplicates are possible, but we try hard to filter them.
So here's the final thought. Consider a truly critical notification, not just a like, but maybe a major security alert, suspicious login detected from a new device. Or maybe confirmation of a high-value financial transaction, like an automated stock trade executing. If our deduplication mechanism fails for one of those messages and the user receives the exact same critical alert twice, what's the real cost? Beyond just annoyance. Yeah, does that duplicate cause genuine confusion? Does it make them second-guess the alert's validity? Could it lead to incorrect action, like trying to cancel a trade that already executed? Does it erode their trust in all future security alerts from the system? What's the actual tangible price in user action, security posture, or financial outcome of that single accidental duplicate of a critical message?
That shifts the problem from just engineering tolerance to real-world user psychology and risk assessment. That's a tough one.
Something to think about. Thanks for joining us for this deep dive.
My pleasure.